6.3b notes for Algebra 2 Honors, and we are going to be looking at logarithmic graphs, and we're going to be using some inverse properties. Remember, logarithms are inverses of exponential functions. Make sure that you pay attention to the directions. 55, 57, 59. Do not use a graphing calculator program or calculator. Do it like I did example 7, showing tables of values. Those will be required on the tests. So, and they need to be done on the homework as well. So, inverse properties, there's some special things. And by the definition of a logarithm, that is log base b of x, that is the inverse of y equals b to the x. So these are inverse functions. That just means if you have g to the x equals log base 3 of x, its inverse function is 3 to the x. So the exponential and the logarithmic of base 3, those are inverse functions. So remember, when you have inverse functions, the points x, y switch. And so if you have xy on the logarithmic function, yx is on the exponential. All right, so they undo each other. So right here, I have log base b of b to the x. You're taking the log of base b, but you have the exponential of b to the x. And so that answer is, that output is just x. You want to memorize that. So if I have log base 7 of 7 to the third, the answer is just 3. Because here you have the exponential, and you take the log of the same base, they undo each other, and you just end up with 3. Likewise, if I do that in reverse, I have base b raised to the log base b of x. The answer is just x. So for example, if I have 8 log base 8 of 5, since this base and that base match, the answer to that is just 5. So you are undoing the logarithm that way. So let's look at these. Right here we have 10 log of 18. Well, again, make sure you copy the original problem down. You need to understand that that is an understood base of 10. So we have this kind of thing happening, where this base matches this base. And so our answer is just the argument of the logarithm. My answer is 18. In this next one, you have to work for it a little bit. 16 is a power of 4. 16 is 4 squared. So write down below it, work down the page, write equals, and I'm going to rewrite this 16 as 4 squared, and then that's to the x. And so then log base 4 powers of powers you multiply, so I can write that 4 to the 2x. And now this base matches this argument, and so the answer to that is the exponent, which is 2x. Okay, for example 6, you're going to need to be able to change forms. Go from exponential to logarithmic or logarithmic to exponential, and you need to be able to do it even if it's a bit abstract. And so in part A, the base is a, so I'm going to write log subscript. Remember, it needs to definitely be a subscript there. And then leave a little space for the argument, and the output of the logarithm is the exponent. So b goes here. And what a to the b equals is your argument, so that's c. So that's going from exponential to logarithmic. And then you need to go from logarithmic to exponential. Lean to the left, lean to the right, equals the middle, get it right, or swoop, there it is. I don't know. Lean to the left, lean to the right. Remember, the output of the logarithm is the exponent, and then equals the middle, the argument. The base raised to the exponent equals the argument of the logarithm. So you need to be able to go back and forth and change forms. So it says in example 6, find the inverse. We are going to rewrite, let f of x be y. And as we did with some linear functions and some other functions, when we find the inverse, we switch x and y. And then we solve for y. But how we're going to solve for y is we are going to be thinking of this as 11 raised to the y equals x. We're going to change forms. The base is 11, so I have log. Make sure that the 11 is a subscript. And remember that the output is the exponent, and what 11 to that exponent equals is your argument. And so we would write it y is equal to log subscript 11 of x. And that is the inverse function. We're just going to leave it y equals in this case. All right, in the next one, we already have y and we have x in there instead of f of x, so it's already in terms of y and x, so we're going to switch x and y. Remember, that's L, and it is not in, it's not an in function, it's natural log function. Or if I put the natural log on the left, x on the right, you have to know that the base of this is e. It's an understood that its base is e when it's ln natural log. And so when we rewrite this in exponential, it is the base. Remember, the output of the logarithm is the exponent, and the base raised to that exponent is what the argument of the natural log function was, y plus 6. But you need to solve it for y, so subtract 6. And be careful. X is an exponent, so make it look like that. And then I like the y on the left. So we have e to the x, and from that we are subtracting 6. So that's your inverse function. Now, there are some problems below here that I suggest that you practice on. So pause the video, do 13 through 18, and see if you did them correctly. See how you did. 13, when these bases match, then the output of this is just that argument of the logarithm. It's x. And on 14, that is when this base matches this base, then the answer to that is the exponent, negative 3x. On 15, you need to start by rewriting 64 as a power of 2. And 64, is 8 squared. And each of those are 2 cubed. So 64 is 2 to the 6th. So I'm going to think of this as 2 to the 6th to the x. So I can write that as 2 to the 6x, and now it's like 14. Now these bases are matching, so the answer to this is 6x. On 16, it's natural log, right? It's not in, it's ln, natural log. It is understood that this base is e. So it's like 13 where those bases are matching. And when those bases match, then your answer is just that argument of the logarithm. 17, find the inverse of 4 to the x. Well, that's a logarithmic function. And the basis for, and remember that the output of the logarithm is the exponent, and what 4 to the x equals is the argument. So there is your inverse function. Except for, oops, I forgot to switch x and y, so I'm going to go back and kind of redo that. My fault. So start by switching x and y. There we go. And then we have log base 4, and the output of that is the exponent, and what 4 to the y equals is x. So there is my inverse function. And then 18, I'm gonna run out of space here. For 18, I switch x and y. And then I'm going to rewrite this in exponential form. And I know that my base is understood to be e. So I have e raised to the exponent, which is the output of the logarithm, equals that argument. And so I get e to the x plus 5 equals y. So I have y is equal to e to the x plus 5. And that is the inverse for 18. Hope you did okay. All right. And we're going to get to graphing. And so we're going to talk about inverse functions are still reflections over the line y equals x. And because if a point xy is on the function f, then the point y x is on the function's inverse. If I find points on f, I can switch the order and I have points on the inverse. And because that's what happens, inverse functions are reflections over the line y equals x. And that also means that the domain and range switch. Whatever the domain of f is becomes the range on the inverse. And so if I look at this on the exponential function, which is this function right here, b to the x, the domain is negative infinity to infinity, and the range is 0 to infinity. That means on the logarithmic, the domain is going to be 0 to infinity, and the range is all reals. The domain and range of the exponential switch. And another important point, if there hasn't been any shifts right or left or up or down or vertical stretches, that on the exponential we have the point 0, 1, so the logarithmic goes through 1, 0. And then on the logarithmic, we have what we call a vertical asymptote. It follows the y-axis of x equals 0. Well, on the exponential, it was a horizontal asymptote, the x-axis of y equals 0. So logarithmics, it switches to the y-axis that acts as an asymptote. All right, and here is an example of the inverses if the base, if it's a decaying function. So if the base is between 0 and 1, then the exponential decreases as you go from left to right. And as you reflect it, then it looks like this on the inverse logarithmic function. Domains and ranges are the same as they were for the base greater than 1. horizontal and vertical asymptotes are the same. All right, so how are you going to graph these? No calculator, folks. So I need to see the steps that I'm going to do here. And so what you're going to do is recognize that the base on this is 7, and you are going to create a table of values for the exponential inverse function. So y is equal to 7 to the x. So start with that base and use -2, -1, 0, 1, and 2. And I'm going to start at the bottom. 7 squared is 49. 7 to the first is 7. 7 to the 0th is 1. 7 to the -1 is 1/7, and 7 to the -2nd is 1/49. You should just know those. And the reason why I did that is because then when I graph this, which is its inverse function, these points just switch. And so I'm going to think of 1 over 49, 1 over 7, 1, 7, and 49. And really, I've got log base 7 of 1 over 49 equals what? Well, that's log base 7 of 7 to the -2nd. So the output of that is -2. And then I have log base 7 of 1/7, which I can write log base 7 of 7 to the -1. So the answer to that's -1. Notice that we've just taken these first 2 points and they've switched places. So then we'll have 1, 0, 7, 1, and 49, 2. And those are points on the inverse. So on that inverse function, at 1/49th, I'm at -2. So you can't even really graph that accurately. So I'm just going to put it close to the y-axis, but not really touching it. And at 1/7th, I'm at -1. So to the right 1/7th, I'm at -1. It's just slightly to the right. Again, we can't be too accurate on that, but we want y to be a vertical asymptote. So I want it to be pulled away a bit from the y-axis. And then at 1, we're at 0. And then at 7, we're at 1. And then we'd be way over to the 40 to 49 before we hit 2. So make sure that you run it parallel to the y-axis, that it comes up, and it just increases slowly. And there is your graph of y equals log base 7 of x. If I drew in the line y equals x and graphed the exponential function at -2, we're at 1/49th, at -1, we're at 1/7th, at 0, we're at 1, and at 1, we're at 7. You might be able to kind of see how the logarithmic function was a reflection of that exponential over the line y equals x. So state the equation of the asymptotes. And so we have for this function, right, we have a vertical asymptote, and it is the y-axis, so it's x equals 0. And you should also be able to state the domain, which is 0 to infinity, and the range, it goes from -infinity to +infinity. Now, a little extension of this, write a table of values for this. Log base 7 of x plus 2. Well, we've already gone through the exponential function and switched it. So we have the parent logarithmic graph for this already. If I didn't, I would start by doing the exponential if it was a different base. And then this means I just need to go take the log base 7 of x and go up 2. So add 2 to y. So my x's are going to stay 1/49, 1/7, 1, 7, and 49, but then we're just going to add 2. So 0, 1, 2, 3, and 4. And there's my table of values. So I just used that one because I already had it. Oops, I forgot to put +2, sorry. And then here, this moves it to the left 3, which means subtract 3 from all the x's. So my table of values for it, since again, I already have the parent, my y values are going to stay the same. And I'm going to shift all the x values to the left 3. And that's going to give me, I'm going to go to the left 3. So 1/49 minus 3 is going to be a minus 2 and 48/49. And 1/7 minus 3 is going to be a minus 2 and 6/7. And then we have 1 minus 3 for the x's is going to be at a negative 2. Then we have 7 minus 3, which is going to be at 4. And then 49 minus 3, which is going to be at 46. And there are the table of values. And so what happens when it goes left is we had on the y-axis was my vertical asymptote, but when I scoot to the left 3, now my vertical asymptote is at x equals negative 3. And so I've got this function going like this. So the domain on that changed actually from negative 3 to infinity. The range is still negative infinity to infinity. All right, that's it.